Okay. I'm hoping this is working. Because this is the first time that I've tried streaming on YouTube. I'm gonna do this. Okay. Audio might be a bit scuffed because I had to redo a bunch of my settings, but hopefully it's fine. It should be fine. I guess we'll find out. Okay, let's put this over here. Okay, I might check out my stream on my phone here just to make sure that it's functioning properly. It looks like it is. All right. Very cool. Very cool. Okay. Back to it. So, what am I attempting to do? Well, I have been working on a couple of programming projects that could greatly benefit from taking advantage of the GPU's multi-threading capabilities. So, problem is, I don't know how to use the GPU properly. So, that is going to be our adventure for today. I mean, ideally, I would be able to create a program that can execute in theory, but I have no idea what I'm going to be able to do today. I know virtually nothing in terms of writing GPU code, but we'll figure it out. So I suppose I just how to write code for GPU. You're gonna hear a lot of my clicking of keyboards because again I haven't updated my whoops, that's not what I wanted to do. Okay, I was trying to move stuff around on my thing, but okay. Check out CUDA by NVIDIA. IMO is the best, or is the easiest platform to do GPU programming. There are tons of cool materials. Let me zoom in on this because it might be hard to read. It still might be hard to read on stream. I'm gonna, hang on, let me pull up my stream again. Because I don't want this to look absolutely horrendous. Okay, stream me, zoom in. Okay, you know what? It's fine. It's acceptable. We're just gonna be super zoomed in today. Okay, there are tons of cool materials to read. How the world would be to do any kind of calculation using GPU. That sounds perfect. Okay, NVIDIA CUDA. What is this? So I have seen this before. I haven't gone into it at all. I am on Windows. I am on 11. Installer type, local, I guess. I don't know. The base installer is available for download. Double click the exe, follow the on-screen prompts. OpenGL stuff, DirectX stuff, sure. HLSL, I feel like I've heard of that before. High level shader language, oh okay. Which is just, okay. No references, you know what, that's fine. Wonder if I can like permanently increase my zoom because I'm at 200% right now. Okay. Download the 3 GB exe and then we'll run it here. I do have on my other screen my task manager pulled up. Let me just double check I'm not giving away any vital info. I don't think I am. So here's my thing. I'm working with an NVIDIA 1030, which is not great. So we are going to be very limited in what we can do, but I've got this pulled up just in case. Okay. Right, it might take a while because, you know, streaming is probably taking up quite a bit of my interwebs. Okay, let's take a look at some of these other answers while we're waiting, I suppose. Second thing that comes to mind is using OpenCL to code for the new lines of general purpose GPUs. I'm not sure how to use this, but my understanding is that OpenCL gives you the beginnings. So let me look at like OpenGL. That's shaderling. Design, development, documentation. That's a fun screenshot. It's just this green text. History. Oh yes, I am truly interested in the history of OpenGL. Actually, it might be legitimately interesting. I was being sarcastic, but drivers, samples, presentations. What are presentations? Interesting. I was more interested in like a code sample, but this is kind of neat. Hardware design. Interesting. This is not a confusing graph at all. Barrier time empty GPU has 2 arrows pointing in opposite directions. Task execution is this weird trapezoid shape. I don't know what these blue lines are for. I'm sure to somebody that's used a GPU before or like worked with one, this makes sense, but oh. Yes, change all of my stuff. Sure. I'll throw that up here somewhere. Pixel shader. Life of a triangle. Now this is what I've been looking for. No, I'm just kidding. I have no idea what this means. I just thought life of a triangle was hilarious. Okay, yeah. License agreement, yeah, sounds good. Express installation sounds perfect. Okay. What is the life of a triangle? So we go into the API. Driver push buffer front end, primitive distribution, vertex fetch, vertex shader, tessellation distribution, viewport processing, rasterization distribution, rasterizer, pixel shader, blending latex, compressed to frame buffer. I don't know what any of this means. This is probably not a great place to start. Because I'm sure those talks are geared towards people who actually know what they're doing. Oh, here are some intros. Welp, okay. What is this guy? Copying and pasting random links from Stack Overflow. Please don't be a virus. CUDA Zone. I hope I'm pronouncing CUDA right. It feels like it would be pronounced CUDA. CUDA is a parallel computing platform and programming model developed by NVIDIA for general computing on graphical processing units. With CUDA, developers are able to dramatically speed up computing applications and harness the power of GPUs. That sounds exactly what I'm looking for. Okay. That might take a bit. In GPU accelerated applications, let me zoom in on this so you can actually read what I'm reading. In GPU accelerated applications, the sequential part of the workload runs on the CPU, which is optimized for single-threaded performance, while the compute intensive portion of the application runs on thousands of GPU cores in parallel. That was a weird way to phrase that, I feel like. But essentially what this means is the CPU does one task after another, while the GPU does exactly that same thing, but it can do multiple instances of that. That's what in parallel means. Just in case you didn't know. That part I understand. I understand that the GPU is good for running a lot of stuff simultaneously. Or like, I don't know, certain things it's good at. When using CUDA, developers program in popular languages such as C, C++, Fortran, Python. Python? Okay. And MATLAB. I didn't realize they supported Python. And express parallelism through... Ooh. Okay, we're still streaming. We're fine. This is all part of the experiment where... you know, messing with my graphics card might end up crashing my stream. Oh, holy moly, my Wi-Fi graph looks funky from Task Manager. Okay, this is all a big experiment. Yep. Great desktop. Launch NVIDIA GeForce. Do I want to launch NVIDIA GeForce? Don't I already have that installed? Don't I have that? NVIDIA. I have the control panel. Yeah, I have GeForce Experience already installed. Why would I want this stuff? Okay. Okay, the CUDA toolkit. This is what we just got, right? This is what I clicked on. Yeah, okay. So we went through this process. Applications developed with it. Okay. Maybe there's like a... So, okay, so I downloaded it. These are features. Customer stories. Is there like a guide? Tutorials. Structured sparsity in the NVIDIA. No. Debugging CUDA. See more. Maybe we can find a tutorial on how to start with this stuff. Debugging. Is there search? CUDA. Topic. I mean, rendering, ray tracing, maybe. Subtopic. Let me just search CUDA. YouTube Premiere debugging more efficiently. This is all about optimizing stuff. And some other fancy schmancy doodads. Okay. I'll search up a tutorial. This is not a great way to go about learning stuff. YouTube tutorials is usually not great. An even easier introduction to CUDA. This sounds like my kind of thing. Who needs easy when you have even easier? This post is a super simple introduction to CUDA, popular parallel computing platform and programming model from NVIDIA. So it said it supported C, C++, Python, MATLAB, and Fortran. But I'm probably going to be using C++. I might switch to Python because it could potentially be easier. But we'll see. I wrote a previous post, Easy Introduction to CUDA. We'll also open that one. In 2013, that has been popular over the years, but CUDA programming has gotten easier. Okay, good news. And GPUs have gotten much faster, so it's time for an updated, even easier introduction. Okay, they haven't said if I need to read this one before I read the next one, but I suppose I'll keep going with the even easier version. CUDA C++ is just one of the ways you can create massively parallel applications with CUDA. It lets you use the powerful C++ programming language to develop high-performance algorithms accelerated by thousands of parallel threads running on GPUs. Is there a way for me to look at how many threads my GPU has currently? It doesn't look like it. At least not in Task Manager. I don't see. Okay. We'll keep going. Maybe I can Google it. NVIDIA 1030 thread count. Memory, board design. There's nothing about thread. There's 1,800 million transistors. I'm not sure how to interpret that. Okay, I don't think this really had what I was looking for. Specifications. Show me threads. What? Cores. Okay, I don't know the difference between GDDR5 and SDDR4. I also don't know if I'm allowed to use cores and threads interchangeably. I mean, there's only one. Oh, these are exactly identical. Okay, never mind. 384 and 380. You probably can't even tell what I'm looking at here. NVIDIA CUDA cores. So these are the specs for my GPU that I'm using right now. So 384. So I assume this means that you can use 300, that it can do 384 things at the same time. Memory speed. I'm just going to assume that's what that means, because I don't know any better. Okay. 384. Many developers have accelerated their computation and bandwidth-hungry applications this way, including the libraries and frameworks that underpin the ongoing revolution in artificial intelligence known as deep learning. This is kind of one of the projects that I was working on that I wanted to take advantage of the GPU with. Not necessarily deep learning specifically, but machine learning. So you've heard about CUDA and you are interested in learning how to use it in your own applications. That is me. This article knows its audience. If you are a C or C++ programmer, this blog post should give you a good start. To follow along, you'll need a computer with a CUDA-capable GPU, Windows, Macs, or Linux. Okay, yeah. Or cloud instance with GPUs. Okay, well, we're doing local stuff. In the future, I kind of want to do cloud stuff, just because my GPU is not the greatest. But we can do that at a later time. You'll also need the free CUDA toolkit installed. Okay, we did that. You can also follow along with a Jupyter notebook running on a GPU in the cloud. Okay, that sounds like not what I want. Let's get started. Starting simple, we'll start with a simple C++ program that adds the elements of 2 arrays with 1,000,000 elements each. Okay. So just some C++ code. Okay, sure. Run kernel on 1,000,000 elements on the CPU. Okay, so this is CPU code. That's kind of what I figured. Free the memory, print out the results. Oh, max error of fmax. I don't know what fmax does, but all values should be 3.0f. Okay, so I assume it's just calculating the difference between the result of adding 1.0 and 2.0 and what it expects to be, which is 3.0. Because floating points, right? Where you add 1 plus 2 and it doesn't make 3. Not confusing at all. First, compile and run the C++ program, put the code above in a file and save it as add CPP, and then compile it with your C++ compiler. I'm on Mac, so I'm using Clang++, but you can use G++ on Linux, MSVC on Windows, or MSVC on Windows. We're going to be using MSVC. Okay, so you did that. Error. On Windows, you may want to name the executable add.exe and run it with /add. Do I need to do all that stuff? Okay, hang on. Let's open up Visual Studio. Create a new project. An empty project. Ooh. Oh, it added a thing here. CUDA 12.2 runtime. A project that uses CUDA 12.2 runtime. I mean, the article didn't say that we needed this. But I'm gonna make one anyway. Cool. Whoops. Yeah, sure, I'll make it capital. CUDA test. CUDA test. Sure. We'll see. Let's see what happens. Ooh, okay. It comes with pre-generated stuff. NVIDIA usage collection. NVIDIA software packages collect usage and platform data via Google Analytics. No, thank you. Okay. CUDA error T, add with CUDA, add kernel. Oh, so is this the exact same thing? Oh, I have an error. Unexpected expression. That's not good. I wonder if C++ 14. I prefer using C++ 20. I don't know if that's an issue. There's a lot more code here than I expected. What is this? Error? Wait a minute. Add with CUDA. You could just wait. You can just like add this block of code into a function here. That's not a C++ thing, is it? That's like a CUDA specific. Oh yeah, this is a .cu. Okay, so this is not. Is it C++? Bro, I can't tell. It sure looks like it. Okay, I don't know what any of this stuff is doing. Let's. No, not a repo. We'll just create a new project. Empty project. Call it add test or something like that. Add test. I like putting test in the names of projects that I know aren't gonna aren't like serious projects that I'm working on. Okay. Oops. Add a thing here. Call it add like they tell me to. Did they uppercase the A? They did not. Whoops. Interesting. It's fine. Add. Okay. And then we'll just copy paste this stuff. Copy and pasting code from online. What could go wrong? Run kernel on 1 million elements on the CPU. Okay, so it's just running this function, right? Sure, okay. They said to compile it. So I'm gonna throw this into release and I'm gonna build it. And we'll see what happens. While that's doing its thing, let's projects, we'll go into here, add test. Oh, I see. Okay, it threw it into 64 release. There it is. Add test exe. We run that. It instantly closes. Okay. Okay, let's go into this directory. This is cd-d and then that. Hang on. Do I need quotes? Probably need quotes. Why is it not working? Is it supposed to be a slash? Okay, there we go. Can I make text bigger on this? Oh, I can. Okay, fantastic. So here's my little thing here. So I just navigated to where this is. To this folder, basically, in my my command prompt terminal doohickey. Okay, so I just run add test. And can I do this? I actually don't know if I'm allowed to do that. Oh, I am. Okay. Max error 0. Is what it printed out. Again, I don't know if it's difficult to see that. Max error 0. I'm not a master at using command prompt, so, you know, forgive me for not being able to do stuff effectively. Okay, run it. So why do you get 0.0000 and I don't? I just get 1 0. I mean, it is printing out a float. Oh, that's right. They like... Didn't they change how floats get printed at some point? I don't remember. On Windows, you may want to name the executable add.exe and run it with /add. Is that a thing you can do? Hang on. /add test. I don't think this is going to work because I don't have the quotes. Right. It's still not recognized. Okay, well, just typing add test exe works. Right, yeah, max error. Dot is not recognized as an internal or external command. Okay, whatever. As expected, it prints out that there was no error in the summation and then exits. Now I want to get this computation running in parallel on the many cores of a GPU. It's actually pretty easy to take the first steps. First, I have to turn our add function into a function that the GPU can run, called a kernel in CUDA. To do this, all I have to do is add the specifier __ global __ to the function, which tells the CUDA C++ compiler that this is a function that runs on the GPU and can be called from CPU code. Ooh. Okay. That's kind of cool. CUDA kernel function to add the elements into arrays on the GPU. Okay. I don't really think it's doing much though. Like, isn't that still running on a single core? Memory allocation. Okay, maybe they're getting to that part. These global functions are known as kernels, and code that runs on the GPU is often called device code, while code that runs on the CPU is host code. Okay, that makes sense. See, because you have to start the program using the CPU, and then the CPU can be like, hey, GPU, why don't you run this code? Okay. So if I go, whoops, like that, it's trying to tell me that that's something that I can do, and it doesn't look like it. Maybe there's, I feel like I'm missing something here. Is there like a CUDA thing? CUDA. No. Okay, I don't know. The article said to add the global thing. I don't know if I just didn't set it up right or what. Or maybe it's, I don't know, maybe it's getting to it. To compute on the GPU, I need to allocate memory accessible by the GPU. Unified memory in CUDA makes this easy by providing a single memory space accessible by all GPUs and CPUs in your system. That's cool. So there's one location that can be accessed by both pieces of hardware. That's handy. To allocate memory, or to allocate data, I was reading this word. To allocate data in unified memory, call CUDA malloc managed, which returns a pointer that you can access from host CPU code or device GPU code. To free the data, just pass the pointer to CUDA free. Okay. I don't know if this is something that I can do in this code though. CUDA, what was it? CUDA malloc managed. Malloc managed. Right. It doesn't like this guy. So if I do this, let me just get rid of this global so it stops yelling at me. Yeah, it doesn't like it. Well, it also can't find N. I don't know. That. Okay. Right. So it isn't a CPP file. Did I maybe not set up the toolkit properly? I downloaded it. Because this doesn't use the global thing, does it? Oh, it does. Okay. So what is this? Define global location. Where is that defined? That is defined in host defines.h. So if I go in here, is that a thing that I have access to? Include host defines. No. Well, what's hang on, what's included in this? These things? Why am I getting notifications? Stop it. Stop telling me there's an update. Okay, I don't have access to this stuff. Now this article has me confused. I don't know what I'm supposed to have access to right now. Okay. I mean, all you did was add this thing, which throws an error. Like, I understand the concept of calling malloc managed and CUDA free. But like, didn't do anything. Do I need to launch GeForce? What was it, GeForce Experience? Do I need to do this and then somehow set up CUDA? Oh, I have a driver available. I'm not going to do that now because that is guaranteed to crash my stuff. I'm not seeing anything. Did I miss something in the installation process? Okay, I assumed this would just fly through because it would automatically detect that I already have the files there. Finally, I need to launch the add kernel, which invokes it on the GPU. CUDA kernel launches are specified using the triple angle bracket syntax. Okay, so that's where that came from. I just have to add it to the call to add before the parameter list. Okay. All right, what's going on here? Yeah, you did all this stuff already. This is just the license agreement. Installs all CUDA components and overwrites current display driver. I mean, I did that, right? Okay, it's telling me I have to stop. I have to stop my code, which I'm not going to do right now. Because I know I have it installed. But it's throwing errors at me. If I try, let's throw into debug mode. What happens if I try to run it? It says that there's errors. Okay, get rid of this. Okay, so it said instead of these two lines, we throw in these guys. And then here's where we free the memory. Free the memory. Okay. Need to launch it. Easy. I'll get into the details of what goes on inside the angle bracket soon. For now, all you need to know is that this line launches one GPU thread to run add. Okay, so I was right. So it only does one thread. Just one more thing. I need the CPU to wait until the kernel is done before it accesses the results, because Kuna kernel doesn't launches don't block the calling CPU thread. Ooh, okay. That's kind of neat, actually. To do this, I just call CUDA device synchronize before doing the final error checking on the CPU. Okay, so it just posted the complete code. Okay, let me just copy paste this. I still don't think it's gonna work because I missed some step of setup. I'm not sure what I missed, because like this is throwing all kinds of errors at me, and if I try to run this, it's gonna be angry at me. Extensions? No, don't do that. Give me full screen. Extensions. Manage. Is there some CUDA thing that I'm missing? I don't think these are right. What am I missing here? Okay, let's go to the easy tutorial, because maybe there's something that I missed. Recent post I illustrated 6 ways to Saxby. What in the world is that? No, don't open it in this tab. Which includes a CUDA C version. Saxby stands for a single precision AX plus Y, and is a good Hello World example for parallel computation. In this post, I will dissect a more complete version of the CUDA C Saxby, explaining in detail what it's done and why. Okay. Sure, this looks fairly similar to what the other thing that we have. The function is the kernel that runs in parallel. Host code. Yeah. Okay, so that's the code. The CUDA C compiler NVCC is part of the NVIDIA CUDA toolkit. To compile our Saxby example, we save the code in a file with a .cu extension. I don't think that was right. Saved in a .cu. Okay. I mean, okay. What does this project have that the other one doesn't? Because this code seems to be fine, save for this. For some reason, it doesn't understand the triple arrow syntax. There's something that this article is not telling me. CUDA files have the file extension CU, so save the code in a file called add.cu and compile it with NVCC, the CUDA C++ compiler. Okay, so I assume that means that Visual Studio is not going to be able to recognize these tokens. Okay, so let's rename that to .cu. It's still not going to pick up on these errors, which is fine. And now it's telling me to compile it. Okay, what are we saying here? Give me out of release. Okay. So we're saying NVCC, I called this add test.cu. Did I? Oh, this is the actual file name. No, I just called it add.cu. Okay. Lowercase a. Add.cu -o add CUDA. NV, oh, I added an extra C in there. Fatal, cannot find compiler cl.exe in path. Okay. CUDA compile error. What was it? Cannot find compilers. Cannot find compiler CLEXE in path. Versions of the SDK after Windows 7 do not include the build tools. If you want to use Microsoft's most recent tools, you have to install Visual Studio. Once installed, you can use the tools from the command line. At the moment, the free versions are the community version. Okay. Continue to develop apps. Seems some bindings for CUDA made for languages outside of C++. Face a problem by including in path before installing Windows SDK. Hang on. Is there something that I need to install here? Build tools. Is there a search bar here? Individual components, CUDA. Great, okay. CL. Okay. Is that a thing? Do I have that? Program files. Program file, is this X? It is x86. We're going to Microsoft Visual Studio. Microsoft Visual Studio. VC is not an option. Now it is. bin is also not an option. What's MS build? Okay, not what I'm looking for. What if it's not in program files 86? What if it's just regular program files? Visual Studio 2022 community. VC. I still don't have a bin. It's telling me I need a bin, but I don't have one. Bin. I do have a bin, apparently. LLVM? What in the world? Tools, MSVC? AMD 64? Can I just do like a general search? It's somewhere in here. And it apparently is called CLEXE. Alright, go on a wild goose chase for me, please. I could have probably added a little specifier that says it has to be an exe file. But okay, let's close out of that because I probably don't need that. Let's also close out of CUDA test. Because I don't think I really want that. Visual Studio projects, CUDA test. I'm going to get rid of that entirely. Okay, here are my search results. Do I have anything that is explicitly... Oh, it's not done yet. Okay, never mind. Doesn't look like I have anything that's explicitly cl.exe. It hasn't found anything yet, at least. Okay. Okay, this is again just code. See if I can find a different answer, maybe. Cannot find compiler. Visual Studio Code is not an official supported development environment. Okay. I mean, it's entirely possible that it did get it installed. I assumed it got installed when I installed the CUDA toolkit. But maybe not. See, people keep telling me it's Visual Studio and then whatever version number and then /vc/bin, but that's not, like, I don't have that as an option. Right, I go in program files, Microsoft Visual Studio, there's no version number here. GPU computing toolkit, CUDA. Maybe it's this bin. No. CICC. Let's search here for cl.exe. Is the other search done? The other search says it's not done. Okay, never mind. CLI.exe, CLI32, CLI64, that's Python stuff. Okay, it has completed the search and found nothing. Oh, hang on. Look at all this stuff. Okay, so this is Visual Studio 2019. Why is Visual Studio 2019 on here? Can I go to open file location? Okay. Well, that's x80. Whoops. What about x64? Does this have a cl.exe? Did I pass it? There it is. cl.exe. Is this the thing that I'm supposed to be using? Okay, that search result failed. Let's throw that into a new tab. Go back to the search results here. Is it gonna research everything? Bruh. Okay, well there was, let's go back to MSVC. So we went into 14.36. Let's go into this one. Bin host x64. See, there's another cl.exe. I don't know which one I'm supposed to be using. I mean, this is, I'm going to assume it's this one. So I'll copy that. Edit my path. Pop a new thing in here. Okay. Now let's try this. Cannot find compiler cl.exe in path. Maybe I have to restart. Command prompt. Okay, go to this. Go here. And then what was the command they had me do? This guy. nvcc add cu -o add CUDA. Creating library, add CUDA lib, and object add CUDA exp. Okay. This kernel is only correct for a single thread, since every thread that runs it will perform the add on the whole array. Moreover, there is a race condition, since multiple thread Multiple parallel threads would both read and write the same locations. Note, on Windows, you need to make sure you set platform to 64 in the configuration properties for your project in Visual Studio, which we are. Throw into release. I don't think that's going to change anything. Is there some property that I'm missing here? VC++ directories. Release 64. Hang on, if I select that, is it gonna understand what I'm trying to do now? No. Okay, it still didn't get it. Compile? Okay, I didn't expect that to change anything. Okay, go back to this. I have no idea what I'm doing here, just for the record. But I feel like anybody that does know what they're doing, that would have been apparent already. Okay, I mean, it did something. I don't know what it did. Add CUDA-exe. Isn't that the thing we did before? Add CUDA. I'm gonna close out of all this stuff. Okay, so it definitely said it created these two files. What if I get rid of all three of these and then go back and run this? Yeah, oh, okay. So that exe was generated by compiling it. Okay. So in theory, this exe file does actually make use of the GPU. Let's take a look at this graph. Look at this graph. And let's see if we get a spike in activity. I'm not entirely sure in which of these things we would get that activity spike. I'm gonna throw this window over here. Okay. Okay, executing in 3, 2, 1, go. I couldn't tell. I don't think we're gonna see anything on that graph. Okay, that's fine. In theory, you know, it actually did all this stuff on the GPU. I don't know if that actually happened. Profile it. I think the simplest way to find out how long the kernel takes to run is to run it with nvprof, the command line GPU profile there that comes with the CUDA toolkit. Just type nvprof and on the command line. Okay. So what are you telling me to do? nvprof /add CUDA. Code execution cannot proceed because CUPT64 DLL was not found. Reinstalling the program may fix this. Ooh, is that because... Hang on. Is that because I started this installation thing and didn't actually finish it? And now it's getting mad at me? Okay. Be that way. Above is the truncated output showing a single call to add. It takes about half a second on an NVIDIA Tesla K80 accelerator and about the same time on an NVIDIA GeForce GT 740M in my 3-year-old MacBook Pro. Let's make it faster with parallelism. Okay. Let's wait to do that before this finishes, because I think I may have screwed something up. What was the error that it told me? Why is it not? Oh, because it popped up a window. CupT64, CupT64 2022. Oh, what was the, hang on. Is that the error that we're getting here? I mean, something like it. Just go to environment variables, select path, add the following. NVIDIA GPU computing toolkit. Okay, let's confirm that that actually exists in the location that we think it does. Program files. We're looking for NVIDIA GPU computing toolkit, CUDA, top 2. And then we need extras. Extras, CupT, lib64. And that's the DLL that it was looking for. So let's add this directory to our path variable. Path, edit, new, paste. Okay. Let's cancel that because I think I figured out what the problem was. And now let's try it. Oh, right, we gotta restart command prompt because command prompt is a lovely tool that I shouldn't complain about. All right, take me to this directory. Take me away to this directory. And then what was the command that we were trying to running? nvprof. nvprof /add CUDA. CO. Oh, I see, because the window is weird. Wait, what? Shouldn't it have this little arrow bracket here? Am I crazy? Hang on, what's going on? PowerShell, are you any better? Do I still have the thing pasted? Okay, I still have the thing pasted. Okay, CD. Get me into this location. That's apparently not how it's done in this. Is it -D? Okay. Thank you, PowerShell, for being different. Okay, so nvprof /add CUDA. There we go. Okay. Holy moly. All right. So what is it saying? Total time 6 milliseconds. For something. Name count. Oh. That's weird. This is formatted weird. But I think I understand what it's trying to tell us, right? Oh, I see. Okay, it was wrapping around weird. Okay, so host to device, 6 milliseconds, and then device to host is 98. Okay, so what is it trying to tell me here? Oh, it actually had like the name of the function. Oh, there's all this stuff up here. I'm dumb. Okay. So here's the add function. Max, min, average. Oh, this is all the same because it was only called a single time. But it took 265 milliseconds. $265 milliseconds. Took half the time that this person's did. I didn't realize my GPU was that fast. Okay. Haha! Take that, article writer. I'm sorry. I take it back. I didn't mean to make fun of you. Please teach me more. Alright, picking up the threads. Now that you've run a kernel with one thread that does some computation, how do you make it parallel? The key is in CUDA's arrow 1 comma arrow. No, sorry. Arrow 1 comma space 1 arrow syntax. Perfect. Just the most readable syntax ever. I couldn't think of anything better, so I'm just throwing stuff. This is called the execution configuration, and it tells the CUDA runtime how many parallel threads to use for the launch of the GPU. There are two parameters here, but let's start by changing the second one, the number of threads in a thread block. CUDA GPUs run kernels using blocks of threads that are a multiple of 32 in size, so 256 threads is a reasonable size to choose. Okay? If I run the code with only this change, it will do the computation once per thread rather than spreading the computation across the parallel threads. To do it properly, I need to modify the kernel. CUDA C++ provides keywords that let kernels get the indices of the running threads. Specifically, thread idx.x contains the index of the current thread within its block, and blockdim.x contains the number of threads in the block. I'll just modify the loop to stride through the array with parallel threads. Okay. So I understand the concept, but this is weird syntax. The add function hasn't changed much. In fact, setting index to 0 and stride to 1 makes it semantically identical to the first version, right? So thread index, okay. I'm still a little bit confused. Why this works. So this is the max size of these arrays that are getting passed in. I understand that it's going from the current thread index and looping through till it reaches the end of the block. No. Oh, hang on. Okay, so it's starting at the current thread index and it's incrementing by the block size. So like, that's weird. So like if you have 2 blocks, it's using thread 1 from block 1, and then the next iteration of the loop uses thread 1 of block 2. Oof, okay. Maybe it'll get explained later. The add function hasn't changed that much. In fact, okay, read that. Save the file as addblock.cu and compile and run it in nvprof again for the remainder of this post. I'll just show the relevant line from the output. Okay, so let's. Why did I close out of Visual? Oh, right, because I tried to reinstall the thing. Okay. Copy and paste this back into our file. Add test. Okay. I still vaguely understand what you're trying to do here. Maybe my confusion is due to the fact that I'm not entirely sure how blocks and threads interact. I mean, I think I understand that a block holds a certain number of threads. I just don't entirely know why we're traversing the arrays in this way. Okay, so let's not do that. I want to compile it, and I already forgot how to do that. Who's that guy? nvcc add told us to rename the file. I'll do that real quick. Add underscore block. Block, not block. So add block.cu -o, whoops, -o, add CUDA. Okay, very nice. That should be compiled. Add CUDA, yep. Okay, and now we run it using nvprof./add CUDA. Okay. So now we're supposed to look at this, and it took even longer. It took 292 milliseconds that time, whereas last time it took 265. Oh, because I didn't change this thing. Duh. Okay, let's go to add. 256. Okay. Let's recompile. And now try profiling. There we go. Now we have 2 milliseconds. All right. So, I mean, I'm getting similar results. I'm just not entirely sure why we're looping through the arrays like this. Because how would the array have to be formatted in order for this to work properly? So let's say index is 0, right? And you have a block dimension of 32. right? So you're starting at 0, and you're going until you reach the end of the array, which in this case is what, like 1,000,000? I don't remember what we set it to. 1 with 20 zeros, I think. Or no. 1 bit shifted over 20 times. Whatever this number is. Okay, so some really big number, and then it goes up by 32 every time. So it's only accessing the 32nd element. Or it's accessing the 0th element, and then the 32, element 32, and then element 64. And then I presume, does it tell me here what the actual, I'm going to zoom out so I can read all this info. Count 258. I don't know what that means. Okay, that's a lot of, I'm having to stretch this out super far. Curious to know what the actual block dimension, what this value actually is. I don't know if that's something that I can access and like print to the console or anything. Okay. It's a big speed up, 400 milliseconds down to 2, but not surprising since I went from 1 thread to 256 threads. The K80 is faster than my little MacBook Pro. Let's keep going to get even more performance. Okay. Even more performance, apparently. Out of the blocks, CUDA GPUs have many parallel processors grouped into streaming multiprocessors, or SMs. Each SM can run multiple concurrent thread blocks. Okay. As an example, a Tesla GPU based on the Pascal GPU architecture has 56 SMs, each capable of supporting up to 248 active threads. To take full advantage of all these threads, I should launch the kernel with multiple thread blocks. Sure. Let me look up. Let me look up my GPU specs again, because maybe it actually had that info somewhere. Because all I saw were these cores. Thermal and power specs. Boost clock. I don't think this is right. I don't think any of this is right. Clock speed, memory, render config. SM count 3. What did this say? It says 56. Okay, dude. All right. I get it. I'm sorry I made fun of you. I'm sorry. Okay, you have 56 blocks. I have 3. apparently. I don't know what any of this other info is. What's ROP? GPU ROPs. Render output unit. Okay. What about TMU? TMUs. Texture mapping unit. Okay. Sure. How do I get like the total number of threads, right? I've got 3 blocks, but I don't know how many threads per block. And I don't know how to figure that out. Is that info on my thing here? I don't see it. Okay. By now you have guessed that the first parameter of the execution configuration specifies the number of thread blocks. Right. Together, the blocks of parallel threads make up what is known as the grid. Since I have n elements to process and 256 threads per block, I just need to calculate the number of blocks to get at least n threads. I simply divide n by the block size, being careful to round up in case n is not a block. Okay. I assume he's going to give me the total code. No. Okay, I'll just throw this in there then. I'll put it here. So here we have add, oh, I see. Okay. So there's that. Okay. So 1,000,000 plus block size minus 1 divided by block size. Num blocks. So that's, I mean, that's going to be slightly above 1. Right? Because n is a really big number. No. No, it's... What is it going to be? I mean, n is... No blocks. Are we sure this calculation is correct? Grid dim x 4096. Why is it 4096? Is this grid dim x the same thing we're using up here? No, that's block. Okay. Okay. So the grid dimension x is the number of blocks? Block index times block dimension x plus thread index x. Okay. So what is this doing here? Block index. Okay, let's say that's 2 times block dimension x. Which in this case is 256, because that's block dimension x is the number of threads in a block. So the number of threads in a block multiplied by the block index. And then plus, okay, I see. Okay, so this little multiplication puts us at the beginning of the correct block. And then we need to go however many in the thread. So that's okay, that's what that's saying. Gotcha. Okay, so let's update our index and stride thing here then. The updated kernel also sets stride to the total number of threads in the grid. This type of loop in a CUDA kernel is often called a grid stride loop. Okay. Save the file as add grid. I don't think this renaming is necessary, but I'm going to do it just to appease the article. Okay, so let's do it again. Am I... What happens if I just run that? I think the exact same thing happened. Okay, so it's not telling me to compile it, which maybe he mentioned before. Oh wait, did I? Add grid. There we go. There we go. Okay. Now we get a speed up. So now it took 907 US, which I think is microseconds? Is it nanoseconds or microseconds? I don't remember. Microseconds notation. Microsecond. Yeah, it's like this US thing. Simplified to US when Unicode is not available. Yeah. Okay, so it's microsecond. So it's 1/1,000,000th of a second. So it's 900 millionths of a second. Okay, cool. That's another 28x speed up from running multiple blocks on all the SMs of a K80. We're only using one of the 2 GPUs on the K80, but each GPU has 13 SMs. Note the GeForce in my laptop has 2 weaker SMs, and it takes 680 microseconds to run the kernel. Okay, summing up, here's a rundown of the performance of the 3 versions of the add kernel on the Tesla K80 and the GeForce GT 750. Okay. As you can see, we achieve very high bandwidth on GPUs. The computation in this post is very bandwidth bound, but GPUs also excel at heavy compute bound computations such as dense matrix, linear algebra, deep learning, image and signal processing, physical simulations, and more. Okay. To keep you going, here are a few things to try on your own. Let's maybe check this out because I'm still having a bit of a hard time wrapping my head around why we're looping through the arrays in such a fashion. Like why does this index need to jump from block to block, right? That's what I'm not entirely understanding. I'm also not entirely sure. Do I need to understand what's happening? I mean, I have enough info here, I think, to kind of do what I want. So it starts at the proper thread, and then for whatever reason it like, oh, this is grid dimension. Block dimension times grid dimension? So what is this stride doing now? So this is the number of threads in a block, and this is the number of blocks in a thread, or blocks in a grid. So this, in theory, is the total number of threads. Stride, why are we incrementing by the total number of threads? That's what I don't understand. Oh, I understand now. I think. So let me go back up to here. So what it's doing, let's imagine that each one of these little rectangles is an element of our million count array, right? So we have an array here with 1,000,000 elements in it. So what it's doing is it's taking the total number of available threads, and it's saying, okay, thread number 0, you're gonna deal with index 0 and whatever the next thing is. So each thread is dealing with its current the element in the array that corresponds with the thread's own index number. And then moving forward through the array by multiples of that. I don't think that's right. I don't think I phrased it right. I've got it in my head. So, okay. So let's say we have 2 available threads, right? And here, this is our array. So the first thread would go to the first element, and then it would go to element index 2, and then element index 4, and then element index 6. And the other thread would do all the odd numbered ones. So then if we had 3 threads total, the first one would do 0, 3, 6, 9. The second one would do 1, 4, 7, 10. And then the third one would do 2, 5, 8, 11. I don't think that made much sense. Here, the good old tool of MS Paint. So if we've got a thing here, I'll just split it up. It doesn't need to be perfect. This is for demonstration purposes, just so I can confirm that I actually know what's going on. Oh, whoops. Text, there it is. 1, make it really, oh, it is really big. Okay, perfect. 2, 3, 4, 5, 6, 7, 8. Okay. So and then here we have the number of threads, right? So let's say we just have 2 threads. Okay, so this bottom one are all the available threads, and then the top one is the actual array that we're accessing. So this is the top array is the data, and then this one is the threads. So thread number 1 is going to go to number 1. It's going to access that element, and then it's going to go to number 3, and then it's going to go to 5. And the reason it skips over every other is because it's incrementing by the total number of threads. So because the total number of threads is 2, it's incrementing by 2 every time. And similarly, the second thread is going to increment by 2 every time, except it's going to start by looking at this one. And then it's going to go to number 4, and then it's going to go to number 6. Now, if we have 3 total threads, 1, 2, 3, first one's going to go to number 1, and then it's going to skip 3 places because that's the total number of threads. This is going to go 1, 2, 3, and the next one it's going to access is element 4. And then number 2 is going to go 2, go over 3, and then access 5. And then the third thread is going to start at 3, go over 3, and then access 6. Okay. But because the threads are not just in an array like this, they're not just all in order. I mean, they are, but they're structured. Because they're not like nicely set up in this array, we have to do this math in order to figure out, okay, so this calculates the index. So this line actually calculates these numbers that I've put down here. This 1, this 2, this 3. That's what this line is calculating. And then the stride is just the total number of threads. So that's calculating the length of this whole array down here. And then it's looping through in the manner that I just displayed. Okay. Okay. Sorry, for some reason that kind of threw me off, and I couldn't understand it for a second, but I understand why now. This is called a grid stride loop. Okay. Cool. Whoops. Didn't mean to open that. Okay. So let's check out the the follow-ups, maybe? How to implement performance metrics, query device properties, using shared memory. Okay. I don't know about all this, but let me see if I can understand what's happening here. So I want to modify this in some way. To kind of showcase that I know what's happening, I suppose. I'm still not entirely sure. Okay, maybe this is where I should do next. Because I'm not entirely sure why this block, num blocks, is equal to this. Okay. Can I just run this straight up without that? Command was not found. Run it as an exe. Oh, I see. Okay, I'm the differences between command line and PowerShell, I suppose. Okay. So there we go. I ran add CUDA exe, it gave me the max error, and it did so in a certain amount of time. Okay. I was just checking to make sure that this print actually functioned properly. So what's interesting is we're doing the addition. So we have two giant arrays, and we're adding each of the elements of those arrays. And we're using the GPU to do that. And then for this error checking, we're just manually looping through the array anyway. So it's like, okay, dude. Kind of getting rid of all of the performance benefits. Right. So what happens if we just remove that? And then we'll recompile it here. And then profile it. Okay, so time it took to call add was still the same, which makes sense. Do we have like a total time? 6 milliseconds and 64 milliseconds. What was the previous one that we said? 797. Okay, yeah. So this one, it went from 97 to 60 something, 64. Okay. So we saved a couple of milliseconds by not calculating that error. I was expecting to save more, to be honest. I was definitely expecting to save more time. Oh well. Okay, I am a little bit bothered by the fact that it gives me these errors. I did see something about using VS Code. So does VS Code have like an extension for CUDA web GPU? I just want like the syntax stuff, right? CUDA C++ language support. Let me generate Doxygen document. Oh, that's weird. CUDA C++ language support for Visual Studio Code. I mean, it has 181,000 downloads. Let's check it out. To maximize compatibility with existing popular themes. Okay. Can I go to like repo? This was last updated 6 years ago. So maybe it doesn't work. I mean, it is a little bit annoying. Maybe I can Google this, hang on. Visual Studio CUDA IntelliSense, there we go. Lots of dust on this thread. I came up with a macro fix for this that I thought I would share. NVCC does not seem to like Visual Studio provides IntelliSense for C++. The trick from the Rocket Scientist blog is basically relying on the similarity CUDA C has to C++. The C++ language, the proper parsing of angle brackets is troublesome. Okay. Switch from the runtime API to the driver API. The C++ is just C++, and the CUDA is still sort of C++. There is no triple angle bracket badness for the language parsing to have to work around. Switch from the runtime API to the driver API. Okay, I don't really know that helps me a whole lot. I'm gonna copy this because when I installed the CUDA stuff, if I say create new project, it gives me like a CUDA template. Right? It gives me the runtime template. So the comment suggested I switch from runtime to driver. I don't even know if that, yeah. Include CUDA. Driver functions, driver types. If I just include CUDA, all of it. Let's throw this in there. Include CUDA. Okay, that didn't get rid of the error stuff. Despite the fact that this is a CU. I did that earlier and it didn't work either. Okay. Let's maybe look for a different answer. Visual Studio Code. My environment. Visual Studio Community. It works well on my side. Make sure that your VS 2017 has installed C++ workload. Please try the following. Disable any other third-party extensions under Tools, Extensions, and Updates. I'm going to close out of that. Let's actually remove it entirely. Goodbye, CUDA runtime. Okay, add test. Drop that. Okay. What are you telling me to do? I forgot already. Tools, extensions, and updates. Okay. Tools, extensions, and updates. I don't see that. Text editor? Maybe just extensions? Updates? Visual Studio Marketplace? Installed. Close VS, delete all files. Rename the whole folder? Okay, that doesn't really help a whole lot. It's pretty much just telling me to delete files and then bring back the files. Okay, that didn't help. Maybe this one? Installation guide? Quick start guide. Let's see what this is about. When installing CUDA on Windows, you can choose between Network Installer and the Local Installer. The Network Installer allows you to download only the files you need. The Local Installer is a standalone installer with a large initial download. For more details, refer to the Windows Installation Guide. Okay, well, I got the local one. I guess I assumed that that was the right one, but it wasn't. Perform the following steps to install CUDA and verify the installation. Launch, download, read and accept, select next. Navigate to the samples N-body directory. Open the N-body Visual Studio solution file for the version of Visual Studio installed. What is this? Navigate to the samples n-body directory? Okay. Open the n-body Visual Studio's solution file for the version of Visual Studio you have installed. Why is it wanting me to do this? Hang on. Visual Studio. No, it should be CUDA. Visual Studio integration, build extensions. Is this something? Extension. Installed. How do I mean, this looks like what I'm looking for. It's it says it's an extension. Yeah. Okay. Manually install VS extension. This is for VS Code. I mean, what file type is it? It's not MS build extensions. I don't know what that means. Maybe I'm thinking the wrong thing, but what in the world is this trying to make me do? I have no idea what that's trying to make me do. When does CUDA setup support VS 2022? Generally not able to answer questions about what will happen in the future or when. That isn't very pleasant. I see a lot of questions in the forum. Okay, I mean, this is all from... These are all posted from 2021. I hope that there's an update. Voila, CUDA Toolkit 11.6 official supports VS 2022. Okay, I mean, like... Sure, they say they support it, but why don't I get the proper, like, syntax stuff? I want the syntax highlighting and the running the stuff. Know what I mean? That kind of stinks. I need VS 2019 in order for it to be supported. Is there no other answer? Installation guide. I don't know. Yeah, I don't know. I'm gonna pin this bookmark. CUDA tutorial. Okay. I mean, technically, I wrote a program that runs on the GPU. And I'm fairly certain this is enough information for me to be able to do what I wanted to do, which is good. But I'm still annoyed that I have all these red squiggles and that it doesn't like save, if it doesn't format the file properly and stuff because of it. So that's unfortunate. But I did successfully destroy my GPU. And by that, I mean I didn't destroy it at all because apparently this was not enough to destroy my GPU. If I run this again, like nothing happened. What if I say what if I say do I have like max stuff? Max long value. Numeric limits. That's what it is. STD numeric limits. Defined in limits. Hash include. Whoops. Limits. And then. So it's that long max. Is that what you're telling me? Seems like it. So let's change this to long and then set it equal to this guy. And then maybe that'll destroy things. Let's find out. Okay, it compiles. Run. GPU utilization is still fairly low. I guess Task Manager was not a great way to... was not a great ruler to measure how well this is doing. Okay, this is taking quite a long time. Maybe this is not a great idea. Oh, utilization 40, 30? Maybe? No. No. No, I don't think anything important is happening. Can I smoothly make it quit? Okay. I think that's fine. I think that worked. Okay, let's maybe change this back into an int. See what happens. Recompile. Run it. Okay, yeah, even the int is taking a while to run now. It would have taken probably several years for the long to get through everything. I'm really surprised it's not telling me that my GPU is being used up a whole lot. I mean, surely this is working properly, right? I hope. It's not doing anything. It's not returning anything. I'm concerned. Oh, because an int is like 32 bits, right? Okay. So maybe not max. Maybe let's just do like 21. So before it was 1 pushed over 20 times. Now it's 1 pushed over 21 times. Let's see if that makes a big difference. It made a decent difference. Now add took 1 millisecond, 1.8 milliseconds instead of 900 microseconds. So it about doubled the amount of time that it took, which is pretty decent considering that we multiplied what is that actually? One with 21 zeros behind it in binary. Hang on. Can I SDDC out? I wonder what this is. If I go 121 minus 120, what actually is that difference? I'm gonna have to recompile and run it again, but did it? Oh, it didn't print out anything. Hang on. Okay, I have to not envy profit. This much. So what is that? That's a million, about. A little more than a million. So we essentially added a million entries, and it doubled the amount of time that it took. Which is that? Is that expected? Is that what we expect to happen? Yeah. Okay. 2. So yeah, we basically doubled the size of the arrays, and it took twice as long for it to execute. I was like, okay. At a certain point, there's only, you know, your limitation becomes the number of threads within the GPU. And being that my GPU is not great, I hit that limit very quickly. Of course, we are saying use 256. What happens if I, like, use some absurd number? Block size. And what happens if I upgrade this to like 512? I'm curious. Okay, let's profile that guy. Still took twice as long. Oh, that makes sense. I should put that back to 20. So we can actually have a fair comparison. Compile and run. Okay, so we're back to 900 microseconds. So not much of a difference changing this number. What happens if we go 128 instead? Compile that, run it. Essentially the same. Almost identical amount of time. Okay. Something really tiny, like 32 maybe? Assuming that 32 is really tiny, but it's not actually. Again, almost exactly the same amount of time. I'm still not entirely sure what this math is trying to do. Because, like, the number of blocks is massive, right? Like, what you know, what is this number here? What is that number? $32,768. I feel like that's wrong. I feel like there should not, we should not be trying to use 32,000 blocks. Like, am I crazy in thinking that? I feel like you should specify the number of threads, right? Or, yeah, I suppose if the second number is meant to be the block size. So block size, and then the number of blocks. Why is it this absurdly large number? Okay. I suppose that does make sense. Because you have to be able to calculate all of this stuff. So it's not actually using that many blocks. It's just like that's what it's trying to use. And then it's using those numbers to help you calculate the index. At least is the theory. I don't actually know how it works behind the scenes. but I suppose that does make sense. It's just weird because this was what, 256? Let's put that back. Put the print statement back. No. I want to compile it. Nope, I want to compile it. There it is. And now we run it. 4096. Oh, okay. So the bigger the block size, the less blocks we have. That makes sense. But like, launch 32 threads. Do not vary across GPUs supported by recent coded toolkits. Demonstrated by the device query sample code. Okay, let's see. Do they have a device query sampler code? Okay, so it seems like my theory was correct in that these numbers, like, it's not actually using a block size of 256. It's just saying, okay, here's an imaginary block with 256 threads in it. I'm just going to use as many threads as I can to simulate what that would look like. And obviously it's not going to be able to run 256 things in parallel, but it's going to try to do something close to that using the threads that it has. I assume is the way that that works. I just CUDA device query. This just keeps telling me I want, like, here we go. How to query device stuff. Memory clock wait. No, I don't want any of that stuff. Compute capability. I want, like, the number of okay. Maybe all of this is imaginary. The GPU doesn't actually have blocks at all. That's kind of where I'm heading. 'Cause this is, I still don't understand. How do I figure out how much stuff my thing has? That's all I want to know. /device query? Where's that? Where do you find that? Device query. Okay, looks like it has some results. I just want to know what my computer can handle. And I don't think I'm understanding what this stuff does. I don't think there's a document that defines these units in terms of a specification. The closest would probably be the white papers that are written to describe each architecture. What is the max number of concurrent threads running on a single core? I think this is a bad way to think about it. A GPU core is not conceptually the same as a CPU core. Okay. CPU core contains all the resources to sustain a C or C++ thread of execution, including things like instruction, fetch, dispatch, register files. Okay. The closest thing on a GPU to that description, in my opinion, is the SM. Okay, we read about that, which is why you can readily find that number discussed in relationship to an SM. Okay. A GPU core, on the other hand, is more closely related to an ALU. Its precise definition is a 32-bit floating point multiply accumulate unit. It doesn't support other instruction types. It does not have a register file itself, etc. So I think your question is not really applicable to GPU cores. If I were forced, I would try to deduce the pipeline depth of the core and report that. But again, I think this line of reasoning is illogical. Okay. Good to know. Thank you. Okay. Well, slightly disappointed by that. I mean, I got this thing working, right? That's all I need, in theory. It runs. It does a thing. I can potentially use it for what I need to. So yeah. A little bit unsatisfying, but I think I'm going to wrap things up. I learned enough for today, I feel like. So that's going to be it. I don't know when I'm going to stream next. This was kind of just like a one-off thing, maybe, potentially. I don't know. I might stream game creation, like making the game that I've been working on, because I've put that off for a while, and I kind of want to get back into it. So maybe